This is the lecture for lesson 34. We're going to continue solving linear equations, but now we're going to go to three variables. So we will determine if a ordered triple is in fact a solution. We will then solve some systems with three variables, and then identify inconsistent and dependent systems, as well as how we write their solutions. The first thing we'll do is determine whether the ordered triple is in fact a solution of our system. We are given the ordered triple 5, -3, -2, and are asked to determine if this works for x, y, and z for all three. So we're now working with three variables and three equations. So just like two variables and two equations, we're just going to plug in what we have and make sure that it works for all of them. So working with this first one, 5 plus -3 plus -2. Is that equal to 0? Yes. The next one, 5 plus 2 times -3 minus 3 times -2. Well, that's going to be what? 5 minus 6 plus 6, which gives me 5, which is what I wanted right there. Yep, so that one works. And our last one, 3 times 5 plus 4 times -3 plus 2 times -2. So we've got 15 minus 12 and then minus 4. 3 minus 4 is -1. So yes, this works for all three. So yes, this is a solution. Next one wants to determine if -1, 3, 2 is a solution for the following three equations. So x, -1 minus 2z is 2. -1 minus 4 is -5. Yep, that one's good. Next equation, y3 minus 3z, so times 2. That's 3 minus 6, which is -3. Yes, that's what we wanted. And the last one, 2x, so -1 minus z is 2. So -2 minus 2 is -4. Yes, works for all three. So yes, it is a solution. Now we're going to solve a system of three equations algebraically. These are very time consuming. I'm going to state that from the beginning. It's very easy to make an error. So we will learn in the next section another way to solve them. For now, we're going to practice algebraically. So right now we have three equations and three variables. What I need to do is I need to get it into two equations with the same two variables so that I can follow the elimination or addition method from last section. What I'm going to do is I'm going to use the first and the second. So I'm going to list them here. So x minus y plus 3z equals 8. Stack 3x plus y minus 2z equals -2. So I'm going to pair those two. And I will then pair the first and third. So I pair first with second, and then I pair first with third. So x minus y plus 3z equals 8. And 2x plus 4y plus z equals 0. All right, so in this first pair, I can eliminate the y's right away if I do my addition. So I can eliminate the y's. So it gives me 4x, the y's are gone, plus z equals 6. So what I want to do now is I want to use that second pair of the first and third to eliminate the y's again and just be left with x and z so that I can use the methods from the previous section. So if I'm going to get rid of the y's here, I need to make this a negative 4y to cancel out with this 4y. So I'm going to multiply this top equation by 4. So I have 4x minus 4y plus 12z equals 32. And the bottom equation is still 2x plus 4y plus z equals 0. And I can add these up now. So 6x, the y's are gone, plus 13z equals 32. So now I have two equations with two variables that I can then work to eliminate. So I'm going to carry these down. 4x plus z equals 6, and 6x plus 13z equals 32. So right now, I see that if I multiply the top equation by negative 13, my z's would be able to cancel out. So top equation, if I multiply by negative 13, I'm going to get negative 52x minus 13z equals negative 78. And the bottom is going to stay as is. Now, if I add the x's here, I get negative 46x. The y's are going to cancel. Negative 13 and 13 cancel out. And then on the right-hand side, I have negative 46. So if I solve for x by dividing, x equals 1. So I've got x is 1. Now I need to get y and z. So it's easy to go back and get z by using this 4x plus z equals 6. So x is 1, so 4 times 1 plus z equals 6. Well, that's 4 plus z equals 6. And if I subtract 4, z equals 2. So now I need to get y. I've got z. So now I'm going to go back and get y. And that's by picking any of the equations from up top. So if we do x minus y plus 3z equals 8. All right, x we know is 1. We don't know y. Z is 2. So 3 times 2 equals 8. So 1 minus y plus 6 equals 8. That gives me 7 minus y equals 8. So if I subtract 7 from both sides, I got negative y equals 1. And then I need to divide by negative 1. So y equals negative 1. So my final solution is 1, negative 1, 2. All right, next trio we have 2x minus 3y plus 7z equals, this should say 25. 3x plus 2y minus 5z equals negative 22. And 5x plus 7y minus 3z equals negative 28. So we're going to start just like we did the last problem. I'm going to write the first and the second paired. And then the first paired with the third. All right. And I see that if I look at this first pair here, the y's are already in opposite signs. So I'm going to eliminate the y's like we did in the first pair. So this one has a 3, this one has a 2. So I'm going to multiply the top by 2 and the bottom by 3. So we just flip-flop, multiply the other one by what it is in the other equation. All right, so on top, 4x minus 6y plus 14z equals 50. And 9x plus 6y, that's going to be minus 15z equals negative 66. All right, so if I work these out here, I've got 13x. The y's are going to cancel. 14z minus 15z is 1 minus 1z. And 50 minus 66 is negative 16. All right, so working with the second pair here, we need to get rid of the y's. So the top one has a 3y, the bottom one has a 7y. So multiply the top by 7, the bottom by 3. We've got 14x minus 21y plus 49z equals 175. Bottom one, 15x plus 21y minus 9z equals negative 84. So now if I add these down, I've got 19x, the y's cancel, plus 40z equals 91. All right, so let's write these stacked up under each other. 13x minus 1z equals negative 16. 19x plus 40z equals 91. So I see the z's are opposite signs, but they're not the same number. I have positive 40 and negative 1. So if I multiply this top one by 40, I should be able to get the z's to cancel out. So 40 times 13, that's 520x minus 40z. Negative 16 times 40 is negative 640. 19x plus 40z equals 91. So if I add these together, I've now got 539x. The z's are going to cancel out. Oops, hold on. I have a mistake here. 14 plus 15 is 29. So this is 29x. This is 29x. I apologize here. This should be 549x. And then on this side, negative 640 plus 91 is negative 549. So make sure you fix that, please. That is a 29, not a 19. If I divide by 549, x is negative 1. I need to find y and z. Well, I can find z using this first equation. 13x minus z equals negative 16. So 13 times negative 1 minus z equals negative 16. Negative 13 minus z equals negative 16. I'm going to add 13. Negative z equals negative 3. So if I divide by negative 1, z is positive 3. And lastly, you can pick from any of the equations. I'll take the first one. 2x minus 3y plus 7z has to equal 25. So 2 times negative 1 minus 3y, we don't know why. 7 times 3 equals 25. So I've got negative 2 minus 3y plus 21 equals 25. Got 19 minus 3y equals 25. So if I subtract 19, negative 3y equals 6. If I divide by negative 3, y is negative 2. You always have the option to go back and plug this into all three equations to make sure that it works, and it will. But there's our final solution. Next trio, we have x plus z equals 3, x plus 2y minus z equals 1, and 2x minus y plus z equals 3. So for this one, I'm going to pair the first and the second with the third. So I've got x plus z equals 3, x plus 2y minus z equals 1. So pair the first with the second, and then I'm going to pair the second with the third. So x plus 2y minus z equals 1. 2x minus y plus z equals 3. Now there's a reason I did this. I picked this way because the middle equation has minus z. first equation has plus z, third equation has plus z. So if I pair the first with the second, already has opposite z's. The second with the third already has opposite z's, and they're just going to cancel out right away. So x plus x, 2x, plus 2y equals 4, because the z's cancel out. And this one here, that's going to give me 3x plus y, the z's are going to cancel out, equals 4. So then I can just stack these guys up. We've got 2x plus 2y equals 4, 3x plus y equals 4. So I can, let's see, if I multiply the bottom one by -2, then the y's would cancel out. So 2x plus 2y equals 4. It's going to be -6x minus 2y equals -8. So now if I add down, 2x minus 6x is -4x. 2y minus 2y is gone. 4 plus -8 is -4. Divide by -4, x is 1. Now we need to find y and z. So I can go to this equation here. 3 times 1 plus y equals 4. 3 plus y equals 4. If I subtract 3, y is 1. And then I need to go back to any one of my original equations here. So let's say I go back to the first one, x plus z equals 3. X is 1. 1 plus what is 3? Well, z then has to be 2. So final answer is 1, 1, 2. Now, again, the way that I am doing it here is not you don't have to do it this way. It's not the only way that it can be done. I just picked the easiest route. Next, we are going to identify if we have an inconsistent or a dependent system. So inconsistent, we're going to get to the point where we end up with a false statement and there is no solution. Dependent is where we are going to end up where we have a true statement and one or two variables can be written in the form of the other variable. So we have x plus 2y plus 6z equals 5. -x plus y minus 2z equals 3. And x minus 4y minus 2z equals 1. All right, so I paired the first with the second and the second with the third. And you'll see why I did that here in just a second. So I do second with third. So first with second, second with third, you see that the x's are going to automatically cancel out. So now I have, if I add 3y, 4z, and 8. And then this one, -3y minus 4z equals 4. So if I take these two and stack them up, 3y plus 4z equals 8. -3y minus 4z equals 4. I see that the y's cancel if I add, the z's cancel if I add, and I'm left with 12 on the other side. So these don't work. This is an inconsistent system. We have parallel lines here, so we have no solution. Next one is x plus y equals 9, y plus z equals 7, and x minus z equals 2. So for this one, I decided that looking at these, so kind of stack them up here. X plus y equals 9, y plus z equals 7, and x minus z equals 2. They're all kind of all over the place. This one only has x and y. This one has y and z. This has x and z. So what I did was I went for a substitution method. And I took this first equation, x plus y equals 9, and said that y equals 9 minus x. So in this equation, I could replace y with x so that I could get x and z and use my elimination from there. So instead of y plus z equals 7, I now have 9 minus x plus z equals 7, which means negative x plus z equals, let's see if I subtract 9 from both sides, negative 2. And then I can stack x minus z and 2 so that I can add these together. So negative x plus x is 0. Positive z minus z is 0. Negative 2 plus 2 is 0. So right there, that is a giveaway that, hey, this is a dependent system. So what I need to do is pick a variable and then solve all the other variables in terms of it. So I'm going to let x be x because y we already solved in terms of x. Y is 9 minus x. And then we need to solve z in terms of x. So now I'm going to use this equation, x minus z equals 2, and solve for z. So subtract x. Negative z is 2 minus x. So if I divide everything through by negative 1, z equals negative 2 plus x. And this is one way you could write your solution. You could rewrite everything in terms of y's. You could rewrite everything in terms of z's. It's up to you. It's just that because I did this first one with x here, I did the other one with x.